Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. This is Module 10, Time Series and Recurrent Neural Networks. This is Part 2. We're going to actually look at the neural networks now and see LSTM and GRU and see how their similarities and differences. So, continuing onward, we are looking at recurrent neural networks. Recurrent neural networks, there's a lot of different types of these. And we'll start by looking at one of the most classic types, mainly because it's relatively easy to understand. And then we'll look at the more modern ones, the LSTMs and the GRUs. There are definitely some similarities between all of these different types of recurrent neural networks. So the recurrent neural networks, they usually have some concept of a context neuron. The context neuron represents a short-term memory. It holds a value between calls to the neural network. So when you're trying to predict with the neural network, that is one call to the neural network. Then you call it again and again and again as you predict row, 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 row. The context neurons start out as 0, but they hold a value as subsequent inputs come to the neural network as a sequence is being processed. So before we saw that we had these sequences that had values for each of the input neurons coming in. These context neurons have a 0 at the beginning of each sequence, and they gain a value and they keep updating their value as these sequences are processed. When you move to the next sequence, this value always goes back to 0. The contexts always go to 0 between sequences. That's a very important characteristic of them. So this is an example of two hidden neurons down here that have context. So instead of simply feeding forward like we have before, we're now going to receive some reflux, some data back from what we're outputting. So you have the input. This is input 1, input 2, going into hidden 1 and hidden 2. These neurons are going to output something based on the weighted sum of values that come into them and then the activation function. They're going to produce some output. And in classic neural network processing, that output would just go on to the next layer or out of the neural network if this was the final. But in this case, we're going to take the same value that was output from the hidden neuron onward, and that dotted line means we're going to copy it to the context. So typically you'll have one context neuron per neuron on the previous layer, and you're simply going to copy the output. There is no weight, there is nothing. It is simply a copy. These solid lines have weights. So what's going to happen is the input to this first hidden one is not just going to be what's coming from the previous layer, but it's going to get the output from context 1. And it's also going to get the output from context 2, at least in this particular case, the way that this neuron is set up, or this network is set up. These are both weighted. So it will learn how to process that value. There's no weighting here, simply whatever was output to the next layer is also copied to here. So you're constantly keeping the value from the previous output from the hidden neuron and allowing that to stay until the next call, and then you copy it back. You let it form the input back to the hidden one on the next call, and it becomes just part of the input. So really, it's like there's 3 input neurons to hidden 1, but 2 of those are the context layers that are just the outputs from the previous one. Now, this output really lives on. It's not like it just affects the next one and so on. Since the value that was copied into this context gets fed back into here, it refluxes. it's almost like butterfly effect. It has an effect on what this neuron's going to output, which then gets copied into here, and it keeps going for each subsequent call of this neural network. That is how the context affects the output over time. And that is what allows the neural network to be time series. And the fact that these solid lines that are causing the copy backwards through the neural network, the fact that they're weighted allows the neural network to learn what to do with this data over time as it comes into the neural network. That is a time series neural network. This is a very classic form of time series neural network. These are not used a whole lot anymore, but this is some of the first types of neural network that I learned recurrent neural networks. This is called an Elman neural network. It was invented in 1990. And this was one of the first types of neural network that could handle time series without any sort of encoding of the previous data. Neural networks before this could handle time series, but it required feature engineering to do it. Usually you take averages of the values over time and feed that into you would do time boxing. There's a whole variety of algorithms that could do that. But now we have a way to have the neural networks do it directly. So I'm going to show you the Elman neural network very briefly, just because this is some of the foundation that this is built upon, and we'll see the weakness in this type of neural network that LSTM and GRU attempt to alleviate. So this is an Elman neural network. Elman neural networks are always single-layer neural networks. This was in 1990. This was the era of shallow neural networks. There was one, maybe two at the most hidden layers, but usually just one. If there's more than one hidden layer, it's not an Elman network. It would be some other sort of simple recurrent neural network. Elman is part of a class of neural networks called simple recurrent neural network. There was another common type called the Jordan neural network, but we won't even get into that one. So you have two inputs, input 1, input 2. You always have biases on non-output layers. So you have the two biases. And in a Elman neural network, you always have the same number of context neurons as you do hidden neurons. So if you notice, there are basically two dashed lines. Those two dashed lines mean exactly what they mean before. It's a simple copy. So the input is feed forward, flowing through this neural network, going through the two hidden neurons into the output. However, what hidden 1 and hidden 2 output are normally the weighted sum that goes into the output neuron, but the values from here and here, literally right after they pass through the activation function on each of these two neurons, is copied to context 1 and context 2. They're not weighted in any way. So those values are copied into C1 and C2, and then on the next call of the neural network, the next row, these values from the previous values of hidden 1 and hidden 2 are copied, are taken from C1 and C2 where they were previously, and they're fed as part of the rest of the inputs into hidden 1 and hidden 2. So that allows learning to occur because these are weighted, and they simply flow on to hidden 1 and hidden 2. And just like before, sort of the butterfly effect, each output is remembered and feeds back into the context neurons and then gets remembered again as it echoes back into it. So that allows the Elman neural network to learn things over relatively short time encodings. Longer time encodings are where Elmans would have trouble. So if you had a whole series of words or something such as that are coming through, by the time you're way out here, you would not potentially have things from the very beginning anymore. So this is an Elman neural network, and that's why hidden 1, hidden 2 both have 5 inputs. Normally, these would have just had 3, input 1, input 2, and the bias on each of these. But you have these extra 2 inputs because it's coming from the 2 context neurons. Now, how do you train one of these? One thing that you always try to do in machine learning research is use what was there before you. So John Ellman was introducing a new type of neural network. That's enough for an academic paper. You don't necessarily want to introduce both a new type of neural network and a new training algorithm at the same time. And he did not. He introduced a new type of neural network and then a small change to backpropagation. And it's really not even a change. It's a way of mapping his neural network into classic backpropagation. And that way, he only has to evaluate how well his new neural network type is actually functioning. The type of backpropagation used on this is called backpropagation through time. So what it does is it realizes that it basically turns this type of neural network, it unfolds it. It turns it into a new neural network that is constantly unfolding as more and more members of the sequence are passed into it. And it unfolds it into a completely regular feed-forward neural network that can be trained with classic backpropagation. And that's how these are trained. Here is an unfolded Ellman neural network. It's exactly this one that we have up here, except it's unfolded. And it's unfolded so that we can actually train it. So here is what this neural network almost looks like in sort of a classic form. You have input 1, input 2, hidden 1, hidden 2. And I did not draw the bias on the output, mainly for simplicity. It probably would have been better to include it, but there would also be a bias neuron. Just basically this guy is missing down here. But there would be a bias neuron feeding into there. Not really germane to the conversation of how backpropagation through time actually works, though. So you would have the two inputs, and this T means the two inputs for the current call of the neural network. T minus 1 means the previous call. T minus 2, if I had it on here, would mean the call previous to that even. So we need to, if you think about it, for the first call of this one, all that's really happening is we have these additional C1 and C2 values. We need those so that we can complete the inputs to these hidden 1 and hidden 2. Well, what are these C1 and C2 values? They're hidden 1 and hidden 2 from the previous call, their values captured and put into here. So that's what we do. We take literally these two context values, feed them in, and then we, from the previous iteration, so we're taking this whole neural network here that was essentially the previous iteration, and we're taking the entire output of this. Notice I have the output neuron with a dashed line around it. That's because we don't care. There's no reason to even calculate it. We don't need the output from the previous calls. We just need to calculate these up to hidden 1 and hidden 2, and then hijack those values and pass them into hidden 1 and hidden 2 to represent the context. And that is basically the values that we need to have in order to have this. Now this is one whole big, this is unfolded just for 2 epochs, but we would unfold it then for 3 and then 4 and then 5. You set some limit up to maybe 10, wherever you want to. It'd be a training parameter. But now we effectively have a bunch of inputs. Now these inputs are just duplicated because, I mean, not duplicated, but they're just previous rows. The current row is the inputs to these two. Previous row is the inputs to these. But it's all one big calculation. And because of that, you can then run backpropagation on it and optimize these weights and train this just like you trained any other feed-forward neural network. We're just unrolling it, unfolding it, and making it one big neural network that we can train normally. Now, the limitation of this type of neural network is that it can't remember things particularly long term. It has short-term memory, but it does not remember them over long periods because the values that you previously had from earlier inputs are just going to slowly sort of decay away as they keep getting refluxed back through those context neurons each time. So we need a way to have both long-term and short-term memory. And what do you think LSTM stands for? Long short-term memory. So LSTM neural networks are a way of having that sort of memory. Now, the really almost layperson way that I can describe this before we go into it really in too much detail would be if we had a scientific sort of calculator. We won't even use any of the fancy features of this calculator. We care mainly about memory plus, remember, and memory clear. LSTM neural networks and gated recurrent GRU neural networks have gates. And these gates are the real innovation of this type of neural network. They let it remember things for a long time or a short time. There are 3 gates that you're dealing with: the input gate, the forget gate, and the recall, or sometimes the output gate. You can think of these gates as dealing with the memory of the neural network or the context. You can think of them as the memory buttons on a calculator. So say we have the output from the neuron is 5. We have these 3 gates, and the 3 gates let you know what you should do. Should you remember it? That would be like memory plus. So I put it into there. We have that 5 now in the context. When it next works, we might need to decide if we should recall it. That's the MR button. That's the output or the recall gate. If you do that, your 5 comes back. And then there's also the forget gate. The forget gate means something happens with the neural network input. It decides it needs to drop the memory, and you can now clear it. And if you do you can't even do an MR because there is nothing remembered. It's important for these recurrent neural networks to be able to forget, and that was a limitation of the Elman neural network. It would just have to slowly forget over time. The other limitation was you couldn't hold something for a long time. So the fact that these new neural networks have the gates, you can remember something and put it into your memory and then forget it later over time. It's often been said, as far as human beings, one of our greatest strengths and weaknesses is to be able to forget. If we remembered everything, our minds would be simply too cluttered and we would not be able to function. The important thing is knowing what to forget and forgetting only things that are unimportant. So let's look at the LSTM neural network. This is a diagram of the LSTM. You have your output, which is essentially y hat, for the current time, previous time, next time. Now this is not 3 different LSTMs. This is the same LSTM, and the LSTM is like a neuron in the network. You'll have multiple LSTMs, just like you have multiple hidden neurons. And you have input. This is the input over time. So you just have a single input value for the current, previous, and next. And over time, the same LSTM over time is passing the y hat to the next one, so the prediction, but it's also keeping a context over time. All these networks have some sort of context, be they Elman neural networks, classic Elman and Jordan neural networks, or be they more modern LSTM and GRU units. Internally, this is what's going on with a LSTM. You've got these gates: forget gate, input gate, output gate. And you've got a variety of clamping or of thresholding functions, sigmoids, and a tan-H. We'll see those in a moment. You can look through this diagram if you prefer. It basically represents the same thing as these equations. I almost like to think of these in terms of the equations, and I'll take you through the equations pretty quickly. This is essentially looking at a this is essentially looking at sort of a linear algebra computation. So you've got the weights. That's the weight F. Weight F is the forget gate. Weight I is the input gate. The bias for each of these layers, so you have bias neurons. And then this vector of the output from the previous one and the input for the current, this is a vector that you're multiplying that weight over. So the first thing that you want to do with this, and by the way, S means a sigmoid function, tan H means a hyperbolic tangent. Before we talk about sigmoid and tan H, let me show you that. Notice the shapes of these. This is a sigmoid function. It goes from 0 to 1, and it clamps these values. So if it's very negative, it clamps it to 0. It's a step function. It's very positive, it clamps it to 1. Hyperbolic tangent, and by the way, this has nothing to do with trigonometry. Machine learning researchers just like the shape of these more so. It's a step function, just another type of step function. But notice that the range is now -1 to 1, so it's got a bigger range. And sometimes we need these negative values, and we'll see when we go through these equations that we do need those negative values. So let's go through the equations. The first thing we have to do is calculate the coefficients for the forget gate and the input gate, and ultimately the output gate. Because these three values, they're going to be largely 0 or 1, because see, these are where the sigmoids are used. You want those to be 0 or 1 because those values, you want them on or off. It's a coefficient. So if the forget gate is calculated to be 0, it's kind of backwards a little bit, but 0 means we should forget. 1 means we should remember. So we calculate the forget gate based on the sigmoid function, which flips it sort of into that 0, 1 range, by looking at the weight for forgetting. So this weight for forgetting, that's the training capability. This value will change as the neural network learns. And by multiplying by the previous output and the current input, that vector, and adding the bias, which is also a learning parameter. So by adjusting these two, we learn when to forget. If F becomes a 0, we're going to forget. If I becomes 1, we're going to remember. So you have the weights. These are exactly the same functions as before. These are your two learning parameters. Those will be adjusted. That's how it learns when to remember, or when to feed the input in. C is your context. C with the little tilde above it just means your candidate context. Now, context is the value that it's remembering. The value that it's remembering is the output from the neuron. The output from the neuron can be -1 to 1. You can't use a sigmoid for that because -1 to 1, it's going to clip off half the values, anything below 0. So that's why we use a hyperbolic tangent. Because the hyperbolic tangent can flow between -1 and 1. So we've got the fuller range of values that we can deal with. But again, the training works just like before. We have a weight for the context, so that's how it's learning what to specifically do with the context. And we have a bias. This is just the candidate context. What really becomes the context is this. And now this is a different format because we're not learning. These are for learning. This is just a switch gate. Notice you have the forget and the input. Input says what should go into the context. Forget means should we remember the previous context. Plus just pipes both of those two together. So forgetting the context, if this is 0 multiplied, it's a coefficient. So if it's a 0, it's going to wipe out the previous context because 0 times anything is 0. Input means, so this kills off the previous context if we're forgetting. Input, and this is why it's like the memory plus button, because this is your previous context. I'm sorry, this one's your previous context. This is the candidate context. So this is what we calculated up here that might be going into the context. If we should put something into, so then the final, now that you've got the output gate created, your final output is essentially going to come from the previous context multiplied by your output. That is essentially how the LSTM is calculated. There's another type of recurrent neural network that is very similar to this that is called the GRU, the Gated Recurrent Unit. It works really extremely similar to this. Let me zoom this in a little bit. This is the academic paper. This is not the academic paper that introduced the GRU, but it's an empirical evaluation of gated recurrent neural networks. Empirical just means experimental. So they're not doing any sort of mathematical proof or hand waving. They're just literally trying it on test data and showing you what a GRU can actually accomplish. In a lot of cases, GRUs and LSTMs function really pretty similar and do sort of have a similar accuracy. This paper deals with evaluating more the processing time. Is a GRU does not have as many gates, and that makes it more simple. So you'll notice in the abstract, they're saying that they evaluated. Also, we found GRU to be comparable to LSTM. And they also evaluated on previous non-recurrent neural networks. So if we look through the paper, the part that I want to show you that is particularly interesting is you have here the LSTM that we just looked at with its gates. You can see the input gate up at the top, the F gate there, and the output gate there. So you have 3 gates. In the recurrent or the GRU, you just have 2 gates, R and Z. So it's a simpler sort of algorithm to that, and it does not require nearly, since there's another gate, it requires much less computation time. And they show you how to calculate these gates. But at the very, very end, the paper gets to showing the learning and showing really that the LSTM and GRU are somewhat equivalent, and they show wall clock time. Notice here the GRU is taking much less time to process than the LSTM. So that's their advantage. You can process much more. Your training epochs will take much less time. Okay, this is the introduction to LSTM and GRU for part 2. And the next part, we'll see how to actually code this in Keras.